Imagine a brilliant software engineer who is trapped in a sensory-deprived glass jar. They have immense computational power, but no hands to type and no eyes to read documentation, and they instantly forget everything they did the moment they blink. This is the exact state of a raw, large language model. A brain by itself lacks the mechanical requirements to execute real-world software development without a human constantly providing context and instructions. To build an autonomous agent, you combine the raw model with its operating environment, the harness. It is the scaffolding that wraps around the model, handling the prompts, tools, memory, and loops that allow the system to finish a task. Understanding this equation changes how we diagnose AI failures. If the system breaks, the problem is rarely the model's intelligence. It is usually a failure in the configuration of the harness. The first architectural step in building a harness is giving the isolated model a body to interact with external data. A persistent file system acts as memory, allowing the model to offload intermediate work. We then add sandbox tools like a terminal and web browser, safely executing code and gathering outside information. However, as tasks grow longer, a model suffers from context rot. As the context window fills up, the model inevitably loses its ability to reason coherently. This diagram shows the harness solution, active context management. The harness uses a technique called compaction to summarize older data and offload logs, keeping the context window clear for the task at hand. Shifting state and memory management to an external harness provides the foundation for upgrading a chatbot into an autonomous system. Even with memory, a single agent suffers from severe overoptimism. It cannot reliably grade the quality of its own work, often finishing a task while ignoring obvious bugs. The solution splits the monolithic harness into specialized personas. A planner agent writes the specification, handing it to the generator to write the code. An evaluator then acts as a strict tester, failing the sprint until the generator resolves all bugs. Think about how you would respond if an agent tries to run a destructive command, like deleting a production database. You shouldn't wait for a smarter model to fix its own behavior. Instead, you insert a hook script into the harness that proactively blocks destructive actions before they can execute. Autonomous reliability depends on the structural checks, balances, and adversarial loops designed into the harness. This iterative approach follows an engineering principle known as the ratchet. This mechanical diagram illustrates the concept. Every time an agent makes a mistake, the engineer encodes a permanent new rule or constraint into the harness to prevent that specific failure from ever occurring. In a mature, well-built harness, successful actions are silent, while failures systematically generate new architectural rules to tighten the system. Let's look at the complete architecture shown in this diagram. To build an agent, you must combine the model and its harness, and use external file systems for memory. You mitigate context rot through compaction, and enforce code quality by using specialized evaluator agents. When these components work together, the results are clear. A decent AI model equipped with a rigorously engineered harness will universally outperform a superior AI model constrained by a weak harness.